Hey everyone, this is Mr. Cure. This video we're going to be looking at intermolecular forces. So I've got a picture here of an experiment you might have done before. And what you do is you take a penny and you add water drop by drop by drop. And basically, it's amazing how much water you can add because the water molecules stick together and they form this little bubble-like shape. It's a lot of water that you can add before finally the bubble bursts, so to speak. So why do we have this? What's going on? Well, behind the scenes, the reason is the water molecules are all attracted to each other. They're stuck together, right? Especially on the surface. You have something called surface tension. And the surface tension holds this bubble in place. And it's quite strong, but it can only withstand so much force. Eventually it's going to break. But there's quite a bit of force associated with this. So why is that the case? Well, remember what happens with water molecules. I'm going to draw a few of them here. Water molecules are polar molecules. We just looked at that right now. And we know because they're polar molecules, they're going to have partial charges. So the oxygen end is more electronegative. It's going to have the negative charge. The hydrogen end is going to be more positive. And that's because of the uneven bonds. You got the polar covalent bonds, making the polar molecule. And the molecules arrange themselves so that the positive hydrogens are close to the negative oxygens. And there's quite a bit of electrostatic attraction between these. And as a result, you have this little network that holds all these water molecules in place. So we have this high surface tension. So that's what's happening behind the scenes here. So these are called intermolecular forces, this attraction between molecules or between particles. They're different from the chemical bonds. So in here, remember, you're going to have polar covalent bonds. These are true bonds, they're really, really strong. And in between here, you've got this attraction. And this attraction is just because of these charges, these electrostatic attractions between oppositely charged poles. So again, in the water molecules, you've got these intramolecular bonds, these true bonds called polar covalent bonds. And between the particles, you've got these intermolecular forces. They're what cause the molecules to stick together and what caused water to be water. So then I've got this. I've got these molecules here. I've got here water. I've got here hydrogen sulfide, very similar size and type of molecule. And finally, we've got oxygen here. Now let's look at what happens. At room temperature, water is a liquid. The hydrogen sulfide is a gas, and the oxygen is the gas. Well, why is that? Well, the reason is because of the attractive forces between the molecules. So if you look at a simulation I have for you here, here we go. This is oxygen gas. And it's not really representative of how fast the particles are going, but you can see that they're quite far apart. And because they're so far apart, there's very little attraction. And also remember, there's no attractive forces or very little attractive forces between the oxygen molecules. They don't have negative or positive charges. Let's look at water. Now water at room temperature looks like this. So the water molecules are zipping around, they're moving, bouncing off of each other, but nonetheless there's a lot of attraction between the molecules, causing them to stick together. And that's kind of what's happening behind the scenes. So when we look at the intermolecular forces, water has a melting point of 0 degrees. And the reason is there's a lot of attraction between the molecules. So the intermolecular forces are quite high. Now, oxygen has very limited intermolecular force. The reason is it has no partial charges. There are no charges on the oxygen molecule. So the melting point is minus 218 degrees Celsius. Now, hydrogen sulfide has a little bit of a polarity associated with it, but not much. A lot less than the water. So because the charges are a lot smaller, there's less charge inequality between the sulfur and the hydrogen. The attraction between adjacent molecules is not as strong. It's a little bit weaker. And because it's weaker, this means that the melting point is a little bit lower. It's easy to separate the molecules. Much, much easier to separate these sulfur hydrogen sulfide molecules than it is to separate the water because they're firmly held together, quite strongly held together. So again, make sure you know the difference between intramolecular bonds. These would be the covalent bonds that are in all of these molecules, or intramolecular. In the intermolecular forces, the forces that occur between these different molecules. So here's a summary table. So intramolecular, within a molecule, extremely strong. They determine the chemical properties. So if you have a chemical reaction, it's because you're breaking these bonds. Intermolecular is between molecules. They're much, much, much weaker, a lot weaker. And they determine the physical properties like solubility, melting point. So especially melting point is what we're going to be focusing on. How easy is it to take these molecules and separate them? That's really dependent on the strength of these intermolecular forces. We're going to be looking at three of them. Three intermolecular forces. We have dipole-dipole, hydrogen, and London dispersion. And we'll be looking at those in subsequent videos.